Alright, a draft physics video production and such. Yeah, it's really draft. A draft on the unification of magnetism, charge, electricity, and even heat. And even nuclear decay, maybe. Probably going to get there. So, all these terms are used. They talk about electromagnetic radiation. They talk about fields, magnetic field and an electric field and EMF and all kinds of different things, and all those things in my opinion are the same thing. They're just slightly different variations on the same theme, and the theme is basically force hits matter and it tells it what to do. Unlike the bent geometry theory that space does this, no, there's actual forces that do it, actual bits of matter. You could argue. I just don't want to really call force matter, but it's stuff, and it's just as real as the electron or the proton. The force is just as real, it's just moving innately, where the matter does not move innately. It has to be affected by a force to move. So, I just sort of wrote down some key ideas. I guess I'll go through some of those and try to explain how all of this stuff is the same stuff. You just have to understand what part of it is identifiable as distinct or different than some other part, where some action is different. So one of the key actions is the difference between light traveling through a transparency. It seems sort of like electricity, and if something goes in one end, it comes out the other end, and a current in a wire. Now, an obvious difference is the fact that light is much slower going through a wire. Now, if you put light through a fiber optic tube, it's quicker, but it's still not going a straight line, so it's still very slow by comparison to electricity through a wire, which can be very fast if the wire is a sufficient conductor and the voltage is the right voltage. Or it's the suppressing of the momentum of the force, the speed of the force, isn't as dramatic in electricity as it is in light photons traveling through a transparent substance. So light is 40%, say, is an average number for transparent substances, water or glass or something like that. And the key thing is that light, what's the difference between light and electricity? So electricity is not frequency dependent, where light is. So some things, they'll be transparent to visible light, but they won't be transparent to infrared or ultraviolet. So I just change the frequency and I change how transparent the substance is. So it's clearly very specific to certain conditions existing, where a conductor is sort of a conductor, and the only thing you can do is make it less pure, and you'll make it less good as a conductor. So you can throw rocks in the stream and slow the stream down, but otherwise the stream is a stream for electricity. So this one's sort of out of place, but anyway, the speed of the jerk in one direction, so that means something to me. It's not going to mean much to you, but so a lot of these systems, you think in terms of pendulum swings, and you think, well, it swings the same speed in one direction as it goes in the other direction. But sort of the way nature works is that you can have a very different speed. That is, you can go this way really fast, and you can go back very slow. And those are two different events in the sense that they happen in a different time scale, and so their measurement of energy would be different if time matters. But where time doesn't matter, it wouldn't make any difference. So it's the same amount of energy overall to go slowly back as it is to go quick forward. Same amount of energy, but for something that is time dependent, It's not the same. It's quite different. If you're only taking a tiny slice of time, the two events have different amounts of energy in them. So I don't know if I need to illustrate that, but the idea is that something, if I did the length of a line, Jesus, this big pen is a pain in the ass, as speed, you could see that it would go back. You know, it could go one direction fast and go back the other direction very slow. I mean, it's going to end up back at the same location, though. So something can jerk, and jerking is different than rolling slow into something. So the real analogy, ultimately, I'm going to get to, is the idea of in pool, if you hit a ball hard, okay, if you move this one fast and hit another one, this one, A, okay, and you have B, A will just take B's place. So A will just stay right where B was, and B will take all of A's momentum and go as if A continued straight through B. So if it has enough velocity, it'll do a pure kinetic exchange where A will hit B, A will take B's place, now A will be here, and now B will be the object moving with the same velocity that A had. And this is, I would argue, is one of the functions inside of a material, is that you can force, okay, of whatever variety comes in, and materials, I would argue, at their surface, okay, translate that force into some action. And the action can be moving an electron slow, I don't know how to draw slow, or moving an electron fast. Okay, and those can be the choices of how the force is translated into two actions. I would also argue that the action could be that the electron just moves a little bit in this direction fast, and then it moves a little bit back slow. So the action is just a small action and a reaction. But this is all just about timing, as I've sort of indicated with the trampoline example. So I would argue that electricity is doing this. So electricity in a wire is really between atoms. As I've pointed out, that's what a conductor is the atoms. You need the atoms, so you need the whole system of electrons and protons. But you need the tension is what you really need. You need electrons to be in positions. And so, I'll clean this up a little. So electricity could be understood as a row of atoms, you know, protons and electrons, and who knows what their exact geometry would be, but they would be in positions where this electron gets hit with enough energy to break it free of this proton. Alright, so sort of indicated before that what happens with these electrons is that as they move through space, their progress is retarded. They lose velocity. So velocity declines with distance. So if they don't move fast enough, that is, if they don't overcome this rebound, so let's call that a rebound, that there's a rebound force that prevents electrons from maintaining a velocity, and so they will be neutralized of their velocity. So unless they get the velocity quickly, that is, unless they're accelerated quickly, they're not going to be able to cover any distance because the velocity is going to be retarded at a certain rate. So if they're hit frequently, fast, like light frequencies, then they'll break free of their proton, and they'll have a momentum, and they'll collide with another electron, force to force essentially. But see, if they're quick enough, then the radiation that's between all of these electrons have a repulsive force between them. But if this impact happens faster than this force can act as a rebound, then essentially this electron A, will do as described. It'll replace this electron. Now A will be here, and B will now do the same thing to electron C. And now B will be here, and C will be the one with the momentum. So electricity moves fast because, faster because it's, now I think I just said it the wrong way. That doesn't help this argument any when I confuse the two. So this is what light is doing. So light comes in at a frequency, a high rate, and the higher, the faster it is, the more likely it is to do this kinetic exchange. So this is what light will do, because the light is little bits of energy close together. Now electricity is bits of energy that might not be at any set frequency. It's just a lot of energy, bits of stuff, but no consistent frequency, so it doesn't hit electrons the same way, so it doesn't move the electrons, actually move them. Alright, so this is light, so let's just be clear. Light does this. And this is why light is slower, is because a good deal of the time the electron's momentum, so we convert a frequency here into a speed here of the electron. The electron speeds through here, but it's not going anywhere near the speed of light. So the electron speed is, half the speed of light. And so it's going half the speed. So the force comes in going the speed of light. It's transferred into velocity of the electron. The electron's velocity is half the speed of light, or more, slower even. And it goes through the material, the transparent material, by this kinetic process. And when it gets to the end, the other surface, so one surface converts the little force bits at a frequency into the speed of an electron, and the other surface, the other end, does the opposite. It converts the momentum of the electron, the electron's velocity, back into a conversion. That is, the electron changes direction to go back home, essentially, and the photon is re-emitted at the surface. So it converts it back into a frequency by basically re-exchanging the same mechanism. The velocity in, and then this conversion essentially means you have to give back what you took here. So you took here a frequency, and now you're going to give it back at this other surface when you change the direction of the electron. But this electron doesn't have to be moving half the speed of light or anything like that. It just has to return to the substance to be reabsorbed as an electron. So it's almost like this is electricity, and the return stroke and this would be your photon as it started off. Alright, so that's light. So light is the movement of electrons. Electrons move slower than force, therefore the reduction in the speed of the photon through the object. So the photon doesn't really travel through the object. The only thing that's traveling through the transparent substance is a velocity, but there's a direct relationship between velocity and frequency. So velocity of an electron as it attempts to leave a substance that is reverse direction will produce a certain frequency. So the faster it's going, the faster it makes this energy exchange as it stays in the substance. It doesn't have enough velocity to actually leave the substance. It has enough to transfer between atoms, but it doesn't have enough to leave the entire substance. But you have to understand the substance has a bunch of protons in it, and there's a huge incentive for the electron to stay in the substance, in the stuff. Alright, this is magnetic, just leave it there. Okay, I got it. Alright, so next, electricity. So I hope that was understandable. So electricity is another thing that happens between the atoms. But what I'm arguing would be happening here is that these electrons aren't hit with frequency tight enough. So they're not hitting it with the energy at a fast enough rate to overcome the fact that the environment itself acting on it, the forces, are going to take away that velocity. So instead of moving enough distance to replace an electron, it just moves out of position. So it goes from this position to this position. Now the difference in those positions can sort of be understood as this distance versus this distance as changing the size of the atom. So you could think of it as a pressure argument. The atom's this size, and then when you move the electron, the atom is this size. So it's been pressurized. So that would be voltage. So voltage is essentially how far are you pushing this electron in this direction. Are you pushing it, if you're pushing it, and so it's a different speed thing. It's not going fast enough to get to the other atom and completely move this, replace the electron. It's a slower push, but it can be a deep push. So it's pushing it bigger and bigger, and that's voltage. So the further away the electron is from the proton, that's the higher the voltage. So and it's a kind of pressure, as I illustrated before. This is the draft part, because there's two parts you can understand this as. So if I have electrons in an arrangement, and it's easier to illustrate with more electrons because I don't have a good diagram of a hydrogen atom, frankly, because we just have to go by what conventional physics tells us is the structure. But regardless, you can sort of understand that there would be this repulsive energy between all the electrons. And as I've pointed out, this is the tension. This electron can't get closer to the protons, because to get closer to the protons, it has to get closer to the electrons. And that's what I would argue is a kind of pressure. If you could push it closer, it can't go closer without there being a negative pressure that gets stronger and stronger. So the more you push, the stronger this repulsion between the other electrons gets. And the more likely it is that that electron will bounce out fast. So that would be how the momentum is created for the electron, is pushing against these forces and having the electron repel from that collection. So that's how you can sort of understand how the frequency goes in, pushes on the electron moves, but it can't stay there because this pressure gets intense, and this rebound pressure is faster than the pressure that went in, you could argue, moves the electron out. So this diagram explains the pressure. Now I'm not saying that's correct, because the pressure could just be this distance argument. So you can also think of it either way. You can think it pushes it into the pressure, or you can think that if this electron got pushed this way, that would create more pressure between these two electrons. Alright, so that can be understood as another way of feeding the pressure into the atom, and now forcing all of these electrons to balance at a new location. So another way of seeing the pressure, these two models both work, is all I'm saying. So I can't say which one is the way it actually happens. You have to think through why one might fail or one might succeed, or one might be more likely or one might be less likely. But to just understand the pressure thing. So if I say a big atom, okay, with the electron further away from the proton, you could argue, so let me just draw the two. Well, I should draw it smaller. So you could have a protons, and then you have an electron at this distance. Now you could argue that this is, regardless of whether this is high pressure and this is low pressure, or this is high pressure and this is low pressure. It doesn't really matter which way you think about it. Just understand that the phenomenon is causing this effect. But you could understand that if the electron is further away from the proton, from something here, this atom will seem more negative because the electron is closer. So say if the atom was neutral, say this is from a distance, you would perceive this atom as neutral. Well, if I change how far away the electron is, you can understand that it can't be seen as neutral anymore. It's going to have to be seen as more negative because of the electron being closer. And if I move the electron further by making it closer to the proton, it would have to appear more positive. So that's sort of the argument. Now, a secondary argument that can be made is that the proton force, okay, the closer I put the electron, the more of the proton force I block. And so therefore the electron becomes stronger because it's closer to the proton. It's blocking the proton force, and so the electron force becomes more positive and it becomes negative. So you can see that either one of these two models work, but the idea of representing or understanding that this is the mechanism that's creating whether an atom is a positive atom or a negative atom just has to do with this relative size thing. You could argue the distance the electrons are from the proton is the thing that's creating the difference between a high pressure and a low pressure atom in a substance. Alright, so once we got that, once you understand that that's all that's happening, is that the atom is absorbing a force in the sense that the force is hitting it, it's changing the structure of the atom, changing its shape, and when its shape changes, that has a consequence. So the consequence is that if I have these atoms, and I have two, say I pressurize this atom, okay, I put force into it, and I pressurize it, and so now it's, bigger. And it's next to another atom, and their electrons interact with each other. When they go by each other, they interact. I think they're probably interacting more directly in the sense that these electrons on this atom are in these locations because these electrons are repulsive. So everything's locked together by distance from protons and electrons. There's always a balance between these repulsive forces, the protons not liking the protons and the electrons not liking the electrons, and there's always a balance between those forces that lock things together. But at any rate, this bigger atom, the pressurized one, is basically going to communicate its pressure between its electrons with the electrons in this other atom, and that pressure, okay, is going to be equalized. So the two atoms, this one blows up, becomes positive, let's say, and this one is certainly, relatively speaking, negative. It's relatively negative to this one's positive. The pressures will equalize. Two atoms will become versions of a mixture of these two. So let's say this was a 70 and this was a 40 pressure. It'll become, 110, and half of that is 55. So these will be 55s. And then if there's another atom over here who's still a 40, well then this 55 is going to blend with that. They're going to become equalized. But now this one's going to be bigger still, so it's going to equalize with this one again. And that's your flow of electricity. Well, I'm off the chart. But that's the flow of the electricity, is just a equalizing of the pressure between the atoms. So it starts off by just balancing this atom, then balancing with this atom, and balancing with this atom. But the consequence of balance is that this one still, if it's getting re-hit, is going to keep repressurizing and repressurizing. So it's going to keep moving pressure from atom to atom to atom to atom. So this is why electricity is much faster, is because electricity is much faster It's because the interaction isn't between electrons moving a distance. It just has to do with the electrons communicating with the other electrons already and just narrowing the distance between them. So the two electrons end up getting a little bit closer to each other. Their repulsive forces, that is the force bouncing back and forth between them, like a ping pong ball between two paddles. I put the paddles closer together. That pressure is going to equalize between all the paddles. So if I put more pressure on this paddle, I'll move this electron a little bit this way. That'll increase the pressure between these. That'll move this electron a little bit this way. But what's happening is the natural state, the comfort zone of these electrons still exists. They haven't moved the protons substantially. So their place where they want to be is still in the opposite direction. So they're going to swing back the other way. So they jerk this way and then they swing back the other way. So that's sort of where I get into the pendulum thing, where they move faster in one direction and then just return to their original position, move faster in one direction, return. So all the electrons are doing in electricity, they're not drifting, they're not moving in a direction. All they're doing is vibrating faster this way and then going back, and fast that way and then going back, and then fast that way and going back, and fast that. So the electrons never go from one place. When they're not banging into each other, they're not traveling. So all that's being communicated is pressure between the atoms, and that's still happening at the speed of the force. So that's why electricity can move through a conductor much faster, is because most of the time it's not moving the electron very far. It's just moving it a little distance. It's not moving it from atom to atom. Damn, this pen. It really is a piece of crap. Sorry. It's irritating. You really can't hold it upright for any amount of time or it goes to shit. So it's not communicating from atom to atom by moving an electron that whole distance. It's just the little bit of force between one atom and another atom. That's why hard materials are better conductors, it seems. I mean, it would give you one reason to believe. That's one of the... What the hell's wrong with this thing? What a piece of crap. Ugh. Sorry. I mean, it's like there's something on the damn frickin' surface, and there shouldn't be anything on it. I erased it. It should be non-greasy. Alright, yes. I'll have to use the other pen, I guess. Anyway. Alright, so the force really won't write. Between is what's communicating the change in the pressure, and the electrons themselves don't move from one place to another place to another place. So light is slow because the electrons are communicating the velocity, are moving the force in the form of their velocity, where in the case of electricity it's just a vibration. The electron moves a little bit in a direction, but it goes back to its position and moves and then back to its position, and it's just communicating the pressure. And so the pressure's not moving straight line, it's probably doing a little bit of this between the atoms, but it gets from one side to the other relatively quickly. Alright, well, take a little pause and be back. Yeah, with more and such. Alright, I should be back and such. Cleaned it off with some alcohol, see if that helps. Anyway, alright, so the speed of the jerk in one direction, I'm just sort of pointing out that the motion doesn't have to be, the rebound motion doesn't have to be the same speed as the force caused action. The reaction doesn't have to happen at the same speed that the action happened at. Alright, so in the key point is surfaces translate, convert force. So these little bits go in, and they can go in the form of a photon, or they can go in the form of something that doesn't have a consistent frequency. So something can have a consistent frequency, or the force can go in, less consistently. I don't know how to draw that exactly, but and the idea is that they're both forces, they're both momentum in a direction, but they'll have a different effect depending on this circumstance. Depending on how they hit an atom will make the difference between an electron jumping position, having enough momentum to have a kinetic reaction with another electron, and an electron just having a weak reaction, in the sense that it rebounds before it can escape its attractive pressures. So it just vibrates in a location, and this one vibrates. So it communicates vibration rather than communicating by actually replacing, by actually using momentum as the difference. So depending on how the force comes in, you'll either have a reaction that is electrical, or one that's more like the transmission of light through an object. Both will involve the momentum of electrons. The thing to understand is both light and electricity affect electrons. The proton doesn't play much of a role. It's only going to be a role that's going to be caused because enough electrons move in a direction, the protons are going to eventually be dragged along by that. But the key fact is that these forces have to do with, this is all electron force. So if as I've explained before, there's two kinds of force. There would be a proton force, and you could argue would be a different color. But these forms of energy, electricity and light, do not contain these red elements in any significant amount. They're not relevant to what's happening. This is what's affecting the electrons, and the electrons are what's affecting or creating the phenomenon of being charged or polarized or pressurized, as I pointed out. And it's the pressure that defines the charge. But we'll get to that. Yeah. Okay. So, let's see, where am I? So, okay, heat can produce electricity. Well, anyway, the surfaces translate, convert the force to electron movement, which changes the force excreted. And by force excreted, I'm just pointing out that the electrons are always excreting a certain repulsive. They're reflecting energy, okay, that's trapped between them. So these are the ping pong balls bouncing back and forth between electrons, and they're always excreting that. And you can just understand, if I move this electron, I move the force of that bouncing ping pong ball to a new location. And if I move it to a new location, it's essentially less distance. So you can understand, less distance means more impacts. Further distance apart means fewer impacts, which means less realized energy. So that argument I've made in the past, you should understand it. Alright, how exactly the surface translates, I won't probably get into that. But again, I've pointed out how surfaces are critical to all this physics. It's a subject completely ignored by physics. Two-slit experiments, almost every phenomenon, refraction, they have no good explanation for how it takes place on surfaces. Surfaces are critical to the interaction between physical pieces of matter, in terms of converting the energy, anyway, and how whether the energy is what effect it's going to have on a substance is completely dependent on surfaces. Alright, so heat can produce electricity, electricity can produce heat. So heat is just a way of describing, here we go again, shit. So all I can say is shit. I mean, I paid money for these damn pens, and it's a piece of shit. So heat, so these are atoms. So heat, in a sense, is the idea of this force between atoms, in the sense that it's really going to be between the electrons, and you can understand, and the protons inside the atoms are the things really reflecting force. So these are the real little bits radiating forces, you know, the protons radiating its forces. And so what's really interacting is the force created by the pieces of the atom, obviously not the atom as a whole. So it's a combination of these two forces. Got the red one down here. So just to be accurate about it, the proton is reflecting the red energy, the electron's reflecting the black energy. There'll be a certain amount of energy in total hitting something. The electron's reactive to the black energy, it reflects it back. So there's a big reflection between electrons, and there's a big reflection between protons and protons. And so this is what's really going to be interacting between two atoms. And heat is basically just saying I've injected more energy or crap between something, or I've brought these two atoms closer together. So either I add more ping pong balls, or I compress the ones that are already between these objects, and so there's more interactions. So heat is just adding more movement. Because that's what this pressure creates, right? That's what these reflections create, is a tendency to move. So if there's not some opposing pressure, this atom will move. If this pressure between the protons gets strong enough, or the pressure between the electrons gets strong enough, it'll tend to move the whole atom. So it gives the pieces of the atom momentum, and the pieces of the atom decide where the atom is going to be. So the atom changes its position based on the pressure between them. So you can understand, the more of these little pieces I place inside of here, and especially the frequency argument, if I have them at a frequency, well, then we know that it's going to cause electrons to jump, and so that's going to even be more aggressive kind of conversion, because now you're going to have a free electron, now free, moving between two atoms, and theoretically some other atom can move in here before this one hits here, and the electron could hit that electron and move that atom, and you know, all kinds of stuff can happen. And that's, generally speaking, what heat is just a form of the force, little bits, not in any kind of consolidated form. Now the trick is that the surface, again, this heat, it doesn't have a set frequencies, doesn't have a lot of stuff, but it does have a lot of movement. And so again, when the atom gets to the surface, it's got to change its momentum. So it's got to go from hitting the surface this way, so to speak, trying to release from the material, and the pressure that's forcing it to stay in the material. And that's again the rebound, and that's where this conversion of direction, an atom moving out of the substance being converted into an atom moving back into the substance, that conversion is the one that creates the photon force that we see. And every atom has its own signature, so the more I heat a substance up, the more of these photons I'm going to see emitted, and they're going to have a certain frequency dependent on the size and how close the atoms are to each other. All that's going to decide what frequency will be produced in terms of the force emitted in this direction to create this direction. And that's essentially what you're seeing as the heat signature. But that's not what's inside of here. This frequency isn't in here somewhere moving around. This has all kinds of vibrations and frequencies, and it's only this U-turn that creates this frequency. Yeah, you sure can't see that in the final drawing, but if you followed along, you followed along. It just explains. The red just doesn't erase very well. but somehow it makes the black stick better, which is good. All right, so the thing I just thought of right before I made this video was nuclear decay, and so I'll get to that because the heat is so critical to what happens in decay. So we have this complex atom, I just draw it, a big atom, and it's radioactive. Well, so it really can't be looked at as an isolated object. So nuclear radioactive material becomes more radioactive, that is, its half-life changes, the more dense I make the radioactive atoms in the substance. So the more pure I make it, and the closer those little atoms are to each other, all of a sudden the likelihood of one of these atoms blowing up goes up. So it goes from 1 in 10,000, to 1 in 400. So the more proximity I create, the more likelihood. So I had always kind of thought that these atoms, when they were created, had a life. They actually had a half-life. So if an atom was created in the sun, then 10,000 years from then, the atom slowly decayed and would collapse. But now I think of it in terms of, no, it's like your body having, let's say there was a patch of 500 cells, and that was a vulnerable spot. And if somebody poked you there, you'd die. Well, the odds of hitting that 500 cell patch is pretty small, right? It's like a little size of a needle or something. And the idea that the needle would hit that little spot is 1 in a million of all the things you're getting hit by. Nothing's going to hit that exact spot and nothing else. The trick is it can't hit something else at the same time. Just that one little spot and none of the cells around it. And so it's like you got a little tiny bullseye on you, a little tiny vulnerability. And that's sort of what these big atoms have, is a little vulnerability. So if you hit them with a high frequency, they'll break and fall apart. So the idea is the closer they are to each other, though, the more likely it is that they are going to do what I said before, like, one atom's interacting with another, and this other atom pushes its electron in. And when it does that, it goes from having ping pong paddles this far apart, and it shoves another paddle in there. And so this frequency, which was just ultraviolet light, before, now becomes an X-ray, because you've cut it in half. Now you'd have to do more than that to create an X-ray, but it doesn't really matter. Point is, you get the idea that the energy can be doubled or multiplied by just creating shorter distances of reflection. And so that's what's really causing the decay, is that every now and then, when these substances are next to each other, through some phenomenon of arrangement of the electrons, say, they have a lot of electrons, so you can sort of understand that a force might go in, hit this electron, hit this electron, hit this electron, hit this electron, and so it has its reflection is multiplied in terms of the frequency of the energy that went in is increased, and it produces one of these high frequency sequences of force, and if that hits another atom, it just blows it up because it knocks too much of its electrons out of place, and the whole thing just falls apart. It splits into two different little smaller atoms, and you end up with a bunch of extra bits that go flying off in the form of these extra electrons. And then they go off and cause more trouble in terms of creating more of this higher pressure that breaks atoms. So it's just a vulnerability built into the complexity that just says, if I put it in an environment where it's going to get hit by heat, it's going to get more and more vulnerable. So that's the key thing, is that radioactive materials become more radioactive the hotter you make them. So the hotter they get, the more likely they are to decay. And the colder they are, the less likely they are to decay. So now we're back to sort of the speed argument, which sews up that nicely. So you can sort of associate velocity with coldness, because velocity is basically saying, instead of moving chaotically into each other and banging into each other, these atoms, velocity is sort of saying that no, a lot of their momentum or energy is being used to move them in one direction. They're all going this way with a velocity. So it takes away this problem, their heat problem, because most of their energy is being is all in the same direction. So they're evading reflections in a way. You could sort of understand that if I'm sending something to this guy and this guy's moving away from me, right? That's creating less pressure. That movement away from me is going to mean that it's less pressure than it would have been if he stayed where he was. So the fact that he didn't stay where he was means that this is going to have less pressure. So it's going to be a colder interaction because this one's not moving. This force is still going the speed of light, but this one's moving away from it. So it's a cooler reaction. So the more you're moving, the colder you are if you're in free space. So something moving in free space isn't hitting other objects, like a bullet going through the atmosphere. Well, it gets hotter. Okay, it gets damn hot because it's hitting a bunch of atoms as it's traveling. So it's crashing into stuff. So that's why a bullet gets hot. But if I shoot the bullet in space, it gets cold because there's nothing opposing this widening of the space between interactions. Interactions are happening less frequently. So the less frequent the interactions, you're going to understand the less likely that a radioactive material is going to decay because there's less energy in the system in a sense. The energy is all moving in the same direction, which means photon can't hit another photon, right? I mean, a photon going the speed of light can't hit a photon going the speed of light. So the more the stuff is moving in the same direction, the less likely it is you are to hit something moving ahead of you, away from you. It's now further away. I said it. So you get it. So this ties into heat, which ties to velocity, which gets us all the way. Not only are we tying electricity to the transmission of light to eventually charge and magnetism, but we've also included velocity and temperature. So it's all tied together. All right, time for another break, I think. So, I mean, I say this is draft, but, this is, this is real physics. It's just, yeah, I should be back. I might have to cut this into 2 parts, actually, to get to all the subject. But we'll see how it goes. It should be the last segment anyway for this video. So conductor versus insulate. So what we've established, what I'm pointing out to you, is that what we're conveying is pressure with electricity. So it's basically a size thing. You can just understand the atoms have different sizes. And a conductor means that the vibrations in the electron, right? The electron is vibrating in a position. Those vibrations are communicated. That is, the electrons between atoms are force connected. That is, the force from this, there's ping pong balls bouncing between these electrons of these different atoms. And so if this one vibrates, that means that this one moves more in this direction, this one moves more in this direction. So they communicate a change in pressure. So however you see that is that this one deflects an electron in, and there's this rebound out. This one will do the same thing. So it's just communicating between the atoms. So a conductor communicates easily between atoms. An insulator doesn't communicate. So it means that an insulator, often the exterior atoms can be pressurized, but the interior atoms won't convey the pressure change. So all the exterior atoms can be all puffed up by a force and essentially charge the surface of an object by forcing all the exterior atoms to become pressurized. Now their pressure, can be either lower, smaller, or bigger. And that would be the difference between plus charge and minus charge. So again, it's all just happening to electrons. Electricity, charge, light is all electron force. The idea, though, is that once you create this charge phenomenon, it will still affect protons in the environment. So you have to still understand that protons are still in the game. It's just that they're in the center of the atom. See, the difference is the electrons are easy to get to because they're on the outside of the fork. You have to go through the outside to get to the inside. So the outside is always more vulnerable than the inside. And so that's why the electron force is so much more important, is because you always have to go through it. You can't affect the proton unless you go through the electron, so to speak. So it's always going to be a player, where the proton might not be a player at all. So it's just a simple diagram of the difference between an insulator and a conductor, is just how well the electrons of different atoms are communicating with each other. If they're not communicating well, it's an insulator. If they are communicating with a lot of energy, then it's a conductor. It doesn't have anything to do with free electrons or any of that stuff. It just has to do with how well the atoms are bound to each other in the terms of how easily pressure is conveyed from one atom to the other atom through the pressure of the electrons. All right. Light and electricity made of electron force, so I've emphasized that. It's all this black stuff. And the red stuff only becomes relevant when you create a dipole, when you put a positive thing right next to a negative thing, and they're not blending their pressures. No proton force directly involved in charge and magnetism. No proton force directly involved. I think that was end of a sentence, period. Okay, charge and magnetism involve both forces. Friction is motion, which adds pressure. The difference in pressure of the atom is a difference in charge. So these are separate sentences. You really can't tell that. So understand, so when I pressurize an atom, I change its polarity. I either make it more positive or more negative. I mean, that's the pressure, the neutral is always just by what the ground state is, So we could say the surface of the Earth has, the atoms of it are communicating with each other. They're a weak conductor, but a conductor. And the pressure is all equalized, and so there's a certain amount of voltage, pressure. And you can either be higher than that or lower than that, and you're going to call one of those more electron pressure or more proton pressure, but there's an actual middle, but the middle isn't something we know. There's an actual change from a positive to a negative, in the sense of more proton force than electron force, but we don't get to see that in everyday life because ground might not be that perfect neutral. But anyway, just all that needs to be understood is what something sees from its perspective. So everything has a viewpoint, right? Everything has a perspective based on what it sees. And so depending on this relationship between an electron and a proton, something will see, from this side I see a negative atom. From this side, okay, I'm going to see a positive atom. All right, so we can understand why the atom looks positive or negative based on which side the electrons are on versus which side the electrons aren't on, or how close they are on one side and how far apart they are on the other side, because the force hasn't moved through them yet. It hasn't equalized yet. So when the force is unequal, one side will seem positive, one side will seem negative. In terms of more proton force will be getting to this side, and more electron force will be going to this side in proportion. So less proton, and this side will have less electron. And so it's really just a mixture of that force that defines polarity, which defines whether or not it's magnetically relevant. Okay, so it's charged, that is, it's pressurized or depressurized. That will tend to make it either positive or negative, depending on what side you're looking at it from. So pressurizing polarizes, which means the atom itself doesn't become completely positive or completely negative, although I think it can, in terms of it can become a monopole, but more importantly it can become a dipole. It can have more pressure on one side than the other, in terms of it can have an imbalance in where there's more negative stuff up here than there is down here. Therefore, it's going to appear more positive. And that's essentially the relationship between pressure and charge. Pressure tends to cause atoms to polarize, and it can cause them to become positive and negative from every perspective, or it can cause them to become positive and negative depending on perspective. So that's a subtle but important thing to recognize. But that's what charge is. And so charge on insulators is just on the surface, and the atoms don't move the charge. They don't convey their increased pressure or their decreased pressure. And so it stays there until some other force says depressurize, till some other atoms contact it and depressurize those atoms and neutralize them, equalize them again, do this thing where two uneven atoms are in contact with each other and they become even. One becomes less big and one becomes less small. And that's electricity. And the phenomenon of being fat and being small, being big and being small, that's charge. So that's the difference between the two. This is a voltage in terms of a potential built out of the fact that you're different. So the voltage is creating a difference, and the difference being neutralized is the movement of electricity. The voltage not being taken care of is a static condition of having a surface that has pressure or having a surface that lacks pressure. I think that explains it. All right. Friction is motion which adds pressure, so you can sort of understand when two substances are smashed into each other and you move them. Okay, you're adding heat, you're adding energy, you're adding the little bits moving around. In terms of you're causing the atoms to move into each other, their force will reflect and compress, and there'll be more interactions, and those more interactions. So if I bring something in proximity to another atom, I move this atom towards this atom, I'm going to automatically create more reflections between the electrons, which will tend to pressurize this atom. Okay, so, and the key thing is depending on what you're moving, okay, what surface is moving, what surface is, who's getting imposed upon. Now it's hard to say whether this, like cat fur or something, versus glass, there's going to be a tendency for it to go one way or the other, because there's going to be a tendency for one to be in a different state than the other to start with, I would argue. But clearly once one side starts charging or pressurizing, you can sort of understand that the other side's going to tend to go the other way because of the fact that these things are repulsive. So if this one has high pressure, fat atoms, and this one has thin atoms, small atoms, you can sort of understand that that's a compatibility. But if this one has big atoms and this atoms are getting big, these two would be repulsive, and so that's not going to work. So it's going to be just like the Kashmir effect. One side's going to go positive and one side's going to go negative, and the bias of the original material is probably going to decide which one goes positive and which one goes negative. And so the motion is basically just going to be converted into pressure. It's going to pressurize one of the sides. And as soon as it makes it more positive, it's going to make the other side more negative. It's not a real transfer, but it sort of is, because you're transferring momentum from one side. The movement of its bits is being translated into pressurizing the other side. So it probably has something to do with what bits are moving more. So this also relates so much to sound. So again, now we're tying it to sound, because it's about moving atoms again, and the velocity of those atoms. And as I've argued, sound really can't happen until you move something faster than the speed of sound. So for you to create sound, it's like that electron has to do that jumping thing again. It has to create enough momentum to break the system. So it has to have enough speed. So you have to go faster than the speed of sound, put enough momentum in the atom itself to make it bounce, replace another atom in a sense. And so the same thing is true, in the small world. There's these speed requirements, and you have to be over a certain speed to have a certain event happen. A certain amount of momentum has to exist, and if that momentum doesn't exist, you won't have the phenomenon of exchange. So sounds, I would argue, all sounds are the byproduct of some little piece somewhere, some atom moving faster than the speed of sound, creating a kind of sonic boom. And so everything we're hearing are just little tiny sonic booms, little tiny things moving faster than the speed of light, causing a sonic boom, which means now the energy transfers very efficiently by atom, like the pool balls, replacing atom. All right. See, it's all related. It all fits. All right. Anyway. All right. Friction is motion adds pressure. Difference in the pressure of the atom, difference in charge. Right. So I think you should be able to get that. Light is transmitted by forcing an electron to replace an electron's position. And I guess I could argue that sound is transmitted by forcing atoms to do a similar thing, to pop the other one out of its place and replace it with no extra movement. Only vibrate electricity, electrons only vibrate faster. So electricity is conveying vibration. The ping pong paddle is vibrating, which means it's forcing the ping pong balls to have shorter and longer distances between the amount of travel, and that's conveyed to the other paddle and causes it to start vibrating. And so the electrons aren't moving from one place to another. So light being transmitted, the electron actually moves and replaces the other electron. All right. Conveying pressure from atom to atom. Okay. Electricity. So this is keywords. Electricity is a process. So when somebody says electricity, that's an event. Okay. That's this pressure thing happening. Low pressure, medium pressure, low pressure. So this is these become the same pressure. That's electricity. Electricity is the neutralization of pressure through atoms. So atoms that are well connected allow the pressure to neutralize between atoms and keep all the electrons the same distance from the protons. And so it's just taking a difference that gets pushed in, and it's saying we don't accept difference. We're the Borg. All our atoms stay the same. We don't allow them to become big and small and do all kinds of crap. We share common blood, you could say. You poison one of us, you poison all of us. That's a conductor. That's electricity. All right. And the light transmission, again, doesn't have anything to do with pressure, really. So anyway. Conveying pressure from matter. Yeah, I did that. Electricity is a process. So electricity is an event. It's the event of equalizing pressure. Charge is a condition. It's the state of the atom. So when it is big, when it's... I hate this damn fucking pen. Yeah, still. Let's see if it draws up there. No. Does it draw down here? Yes. So it draws down there. Alright, anyway. So it's just, where was I? Charge is pressure. So if the atom is pressurized, especially relative to its fellows, then it's said to have a charge. And a substance that is an insulator can have a charge on its surface. Now, if it's a conductor, you can charge all the atoms in the substance, make them all big, okay, because it'll just convey the charge to all of them, so you can just put the charge on the big hunk of metal itself. But insulators will allow you to change that charge. Clearly, in substances in a field, say if I have a field of 2 million volts over here, and this thing's in that field, well, obviously one side is going to be getting a lot more voltage than the other side. And obviously, too, we know that the electrons do move, based on what this voltage is. So if it's plus 2 million volts, then all the electrons will tend to move to this side, and this side will have a lack of electrons because there's no other source of electrons. Electrons aren't out here free. There's nowhere to get any from. Now, the atmosphere does provide them, so that's like having a ground connected to the atmosphere is a weak ground that sucks the energy out of everything, the difference. But the point is when you're charged something by using an external force without touching it. So if I touch it, then we know all of this pressure will leak right out or be pushed right in. But I can't add or subtract electrons if I don't touch it. I can't replace electrons, can't do any of that kind of stuff. So I can't provide more electrons to this place that has fewer electrons, or if it has more electrons, I can't pull them off if I don't touch it. But so obviously the electrons that are in the substance are the ones that will be over here, and the tendency to be over here means there's fewer over here. So obviously these atoms are going to be depressurized. They're going to get smaller, and these atoms will be bigger because there's more electrons in the same area, which means the electrons are repelling each other, which is creating more distance between each other. And that's the polarization of the object. And if I broke the object in half, obviously this side is going to have a lot less electrons in it damn it. This is really pissing me off. I mean, it doesn't mean anything, it's pissing me off. Piece of shit. Yeah. So obviously if I break it in half, this side has got less electrons in it than this side, so yes, this will be negatively charged and this will be positively charged, blah 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 blah. But again, the charge doesn't have really anything to do with, it has everything to do with magnetism, but I'm just saying it has nothing, it just has to do with how far the protons are versus the electrons, and whether the thing as a whole is going to excrete more proton force or less proton force. Obviously, if there's fewer electrons, less electron force is going to be excreted, and the same number of protons, well, then it's going to be more red than black, and this is going to be more black than red, and ergo you have the phenomenon of a dipole. So maybe dipoles need a separate video, but putting the two next to each other in proximity to each other is the phenomenon of magnetism. Magnetism is detecting. Try the blue pen. I might as well just use blue. Maybe it'll do the same fucking thing. Alright, so magnetism. No, I want to keep the blue. Get rid of this black piece of shit. Oh, I put the wrong cap on the pen. Alright. No black. We'll use the red and the blue. Alright. Alright, so the pressurized atom versus the depressurized atom. Alright, so this one has more, we'll say the protons are blue and we'll say the electrons are red, which is probably a big mistake, but whatever. No, obviously this one, okay, the blue one is the one with where the proton's going to be stronger, and this is the one where the electron will be stronger. So I should have made this blue. This red. Well, I don't know. I did the same thing. Well, anyway, they don't look like now it doesn't look. Yeah. Well, anyway, this is the dipole. Is having something that's going to radiate more red. This one will radiate more red, and this one will radiate more blue. And so that's your dipole. And obviously, if I put another dipole in proximity, that's radiating more red from this end, more blue from this end, we can just get to the argument that if I switch that, all the blues would be reflecting back and forth, and all the reds would reflect. It would repel this. And if they're opposites like this is, then all the red leaves the proton strong, and the black leaves the electron strong. Well, whatever, you get it. They're opposites. The force doesn't reflect. There's no reflections here, and so therefore less pressure. It moves away, or it moves towards, because there's less pressure. Less pressure means it moves towards. More pressure means it moves away. And you create pressure by creating similar objects next to each other. So two electrons next to each other. I mean, I've already drawn this thing so many times. But two electrons next to each other, it's all pressure, because this reflecting takes place over and over and over again. The force doesn't ever get out. Well, not ever, but that's the nature of the power of the force. But if it's next to a proton, the electron, then all the force, the proton force leaves the electron perpendicularly. The electron force leaves the proton perpendicularly. No reflections, no pressure. The two move closer to each other. All right, so I've already been over that. So anyway, so electricity is a process, charge is a condition of the atom, a pressure, its pressure. So everything is charged. Everything has a pressure on its surface. So everything has a state of charge. It's a condition. A magnet is automatically connected. A magnet is a atomically connected dipole of charge. So just understand that even if you could make two fake charges, that is, you could charge a substance positive on its surface and another one negative on its surface, you haven't really created an actual atom that transmits that, that has that connection built into it, where one side is positive and one side is negative. So it's not exactly the same as an atomic dipole. I think if you could actually construct them and put them next to each other and do all that crap, you could synthesize magnetism. So yeah, so we made it through most of what was written here. Good. Alright, so I think that's enough for the video. It's the draft video on the subject, as I haven't really attempted to do this, trying to explain how all of this connects, and how these words we're using them like they're separate things, and they're not separate things. It's all based on one kind of condition, force going into atoms, changing the atom into a different kind of atom, and the consequences of that, and how basically electrons react. I mean, this is a key thing, is the momentum argument. You give an electron momentum, and then you have electrons interacting with electrons in a real way, in the sense that they're it's the pool ball example. I roll a pool ball into another pool ball slowly, it doesn't replace it. Both balls end up leaving at some new velocity. But if I do it fast enough, the one ball will take the other ball's place, and exactly the momentum that the first ball had, the second ball will leave with. And that's the story, pretty much, is understanding that phenomenon of motion. It matters how fast something's going to how an interaction will take place between two pressurized objects. If you move faster than the pressure, if you move it at a speed of a certain sufficiency, it will overcome the pressure limitations, whatever you want to call them. So again, I could just argue that sound is basically atoms banging into each other fast enough to replace each other in positions, where and light is electrons doing the same thing. And electricity is just, I vibrate, you start to vibrate, the next guy starts to vibrate. It's just vibrations moving. And it's really the vibration in one direction. It goes this way. And this thing says, go this way. And they're all forced to go back into position because they're tied to atoms. So they're jerked fast, and then they move back. Jerked. And that's what's happening. All right. Yeah, so I've done my job. You know, again, if you're just resistant to logic and reasoning, I can't help you. I can't do anything about that. It seems human beings are. Quite obviously, the world's a piece of shit. It's running backwards. And so you are all fucking idiots, because the world wouldn't be the pigsty it is if you weren't. But all I can do is try to get you to realize that maybe you shouldn't be so arrogant. Maybe you shouldn't be so devoted. There's good cause to question America and its ethics in the world. There's reasons to doubt. And you're clinging to bullshit because some nerd told you so. And that's the real pitiful part. Because a nerd told you so. Shit. Anyway. Okay. Till next time. And such and so forth and whatnot.